So, significant figures. Pennies come in whole numbers. How many pennies are in that picture? 7. Are you sure? Yeah. There are exactly 7 pennies, right? You don't find half of a penny. It's like people. How many people are in my family? There's 8 people. It's not 8.5, it's not 7.9, exactly 8 people. Counting. But other things are non-exact. When we measure the length of something or how much it weighs, is it exact? No, it isn't. So if we look at this gold bar, it says 10 grams. Is that exactly 10 grams? No. How close to 10 is it? Well, it depends on how it was measured. So what we do is we are careful in science to write our numbers so that they reflect the precision with which a measurement was made. So scientific numbers are reported so that every digit is certain except the last one, which is always estimated. So we estimate the last digit. So if we look at this 45.872, the last digit is an estimate. All the digits before it are certain. And you just kind of have to say, oh, well, okay, that's what Mrs. K said. This is how it is. So the first 4 digits are certain. The last digit is estimated or uncertain. This is the pattern for all scientific measurements. So if we look at this balance, which, all of the pictures, by the way, in my PowerPoint slides are from the textbook. They're figures from the textbook. And so even if you don't have a computer at home, you can go home and look at that picture. It's a little hard to see on the screen here. But there are divisions here. This one is marked, the top line is marked 0, and this big line here is marked 10. And there are 10 lines. There's 10 sections in here. That means that each of these lines represents 1 gram. So when we weigh this blue powder here, we can see that it's definitely between 1 gram and 2 grams. The little marker there is between 1 and 2. So we know it's 1 point something. So when we report the mass as 1.2 grams, this first digit is certain. We know it's 1. It's 1 point something. The second digit is estimated. It might not be exactly right. And if you had 5 people look at that, they might come up with several different answers. Somebody might say, no, I think it's 1.3. It's okay. It's an estimate. It's an estimate. It's not certain, and yet it's still information, and we don't want to throw away information. So we're going to include the estimate. So one thing we do, this is an analog scale or balance, just like a ruler is an analog. It's not digital where it just gives you numbers. And it's got lines on it. We always read between the lines. And I'll just hammer that into your brain in lab. Read between the lines. Let's look at another example. Here's another scale. So the markings on this one, here's 1 gram and 2 grams. And in between 1 and 2 grams are tenths. So each of those lines is 0.1 gram. So when we look at this, it's just too small for me to be able to look at. So this is 1.2 something, right? Do you see that? It's between 1.2 and 1.3. So now the 1 is certain, the 2 is certain, and we can guess or estimate the next place. So we look at this balance and we see, oh, the smallest divisions, the smallest lines are 0.1. So we're going to estimate the next decimal place. If the lines are at the tenths, we're going to estimate the hundredths. If the lines are at the ones place, we'll estimate the tenths place. Okay, so we would record that as 1.26. And another scientist looking at this measurement would understand that we estimated the last digit. Everybody with me still? So significant figures are a way to help us deal with the uncertainty in measurements when we do calculations, because crazy stuff can happen when you do calculations. So we've got two options. We can do significant figures, or we can do differential calculus. How many votes for differential calculus? Yeah, I didn't think so. It's a lot harder that way. It's more accurate. Significant figures, which many students do not like, significant figures are just a relatively simple way of keeping track of the error or the uncertainty in measurements. So first of all, we have to learn how to identify which are significant digits and which are not. And so we have some rules. All the non-zero digits are significant. So in this number, 1.05, there are two non-zero digits. Those are definitely significant. In this number, we're talking about this one and this one. Those are examples of the non-zero digits. The students don't usually have a problem with that one. It's the zeros that get tricky. There are three kinds of zeros. Did you know that? They all look the same, though, right? They're zero-shaped. Yeah. There's three kinds of zeros. There's interior zeros. They're sometimes called trapped zeros. These are between non-zero digits. So here we have one here and one here. They're stuck between non-zero digits. Those are always significant, always. This number has a trapped zero. Then we have trailing zeros. Trailing zeros come at the end, right? We read numbers from left to right, and trailing zeros come at the end. These are the guys that are probably the most confusing. The trailing zeros are significant if there is an actual written decimal point in a number. Not an implied decimal point, an actual decimal point. So in this number, we have 5.10. The zero comes at the end, but there's a decimal point. That's significant. 500.0. All those trailing zeros are significant. It doesn't matter if the zeros are before the decimal point or after the decimal point. Trailing zeros are significant if there's a decimal point. If there's an implied decimal point, like this number, 50,000, if we were going to put a decimal point in there, we know where we would put it, right? We'd put it right here after the last zero. 50,000, the decimal point would go right there, but it's not written there. So when we look at a number like 50,000, we're not certain. That's not a good word to use. We're not sure. We can't be sure where the uncertainty in that number lies. Because if that was the number of people who have a blue Prius or something, or the number of people that immigrated in 1927, I don't know, making stuff up. Does that mean we know it exactly? There were exactly 50,000? Probably not. Maybe they measured it or estimated it to the nearest 100 or the nearest 1,000. We can't tell from that number. You know, if I ask you how many people are in Fresno, how many people live in Fresno? What's the population? Nobody has a clue. 500,000. Okay. So that's an estimate, right? Because even when they go through and they take the census, They finish counting, and a baby's born. And then 2 people kick the bucket. It's wrong already, right? It's an estimate. And we say 500,000, it's an estimate. Scientists want to be very careful when we give numbers to each other that we understand where that uncertain digit is. Because we don't want to take something that's just a guesstimate and have someone else interpret it as exactly 500,000 people, right? So what we say is that these trailing zeros with no decimal point are ambiguous. We can't tell. 10, oops. You know, something's 10 feet long. Is it exactly 10 feet? Or is it just about 10 feet? It's ambiguous. So we try to avoid ambiguous numbers. And what we're going to do with those is we're going to, if we encounter them, we're going to assume the large error and assume that they are not significant. And then we have leading zeros. Leading zeros come to the left of the first non-zero digit. Leading zeros come at the beginning. Trailing zeros come at the end. Leading zeros come at the beginning. Leading zeros are not significant. They're important, but they're not a measurement. So here we have 0.0005. We need those zeros in there because otherwise it would be 5, which is a completely different number. But does that imply that we measured something? Because what if I had 52 and I put some zeros in front of it? Would that mean I measured it more carefully? No, it would just look silly, right? Why'd you put all those zeros in front? And if you're going to put that many zeros, why not put 5 more? That's silly. These zeros are important. They're necessary to locate the decimal point. They're placeholders. These trailing zeros without a decimal point amount to placeholders as well. You can't just get rid of them because it changes the value of the number. They don't necessarily reflect measurement. And so these leading zeros don't reflect measurement either. This guy right here. Okay, so those are not considered significant digits. And then we have exact numbers. So measurements are not exact, but there are some exact numbers. And we consider them to have an unlimited number of significant figures. And these sorts of things would include exact counting of discrete objects, like the 7 pennies. We can count them. That breaks down when you get to really, really large numbers, like trying to count 500,000 people, right? Because people die and people are born while you're counting them. So there's kind of some wiggle room in there. But, 5 pencils, 10 fingers, exact. If we have integer numbers that are part of an equation, the volume of a sphere is 4/3, 4/3 pi r cubed. The 4 and the 3 are exact numbers. If we have defined quantities, some conversion factors are defined quantities and others are not. And we'll get into that more later. But 1 centimeter is exactly equal, 1 inch. 1 inch is exactly equal to 2.54 centimeters. Exact. So those are exact numbers. They actually redefined the inch.
I had a question. The 3 lines that you used to equal being 2 single lines?
Right.
And even though the 3 is, does that mean exactly equal?
3 lines means exactly equal to. Yeah. And so sometimes you'll encounter that in a table of conversion factors. And that's to denote that this one is exact. Other times you might see that 1 pound equals 2.2 kilograms. That's not an exact relationship. It's 2.206 or something like that. No, it's actually I did it backwards. 1 kilogram is 2.2 pounds. Got it backwards. Okay, so let's look at these numbers and determine how many significant figures are in each of the numbers. So this first one, 0.0035. 2. Leading zeros are just holding the decimal place. So this has 2. If you don't understand why, please ask me. 1.080. I heard 3 and 4. 4 is correct. So the 1 and the 8 are easy. This is a trapped 0, an interior 0. This is a trailing 0. There's a decimal point. The trailing 0 is significant. Yes?
The first one was only 2. Why was that one only 2?
Good question. Confused because the first one's only 2 and this one's 4. That's because these are zeros at the beginning of the number, and this is a 0 at the end of the number, and we treat them differently. So zeros that come before are never counted as significant figures.
That come before the leading number?
That before the first non-zero digit. So we go from left to right like we read, and any zeros that come before we get to a non-zero digit, 1, 2, 3, 4, 5, 6, 7, 8, 9, one of those, those are leading zeros, and we never count those. So let's that's a hard concept. Let's look at what would this number be in scientific notation. 3.5 times 10 to the what? So I'm taking the decimal point and I'm moving it 1, 2, 3 places. That's a small number, so -3. What happened to those zeros? Why don't I have them anymore? Because the times 10 to the -3rd now is holding the place. Like, well, why don't I put those zeros in there? Is there any reason for them to be there? Do they reflect measurement? No. Let's look at this next guy in scientific notation. But wait a minute, the decimal point's already in the right place. Okay, so maybe that's not a great example. What would that be in scientific notation? If it's in scientific notation, it has to have a times 10 to the something. 0. If we multiply by 10 to the 1, then we're multiplying it by 10. 10 to the 0 is the same as 1. Why do we write that 0? Do we need it to hold a decimal place under any circumstances? No. Why are we writing it? Because we're indicating that that is our estimate of that decimal place, that we think that that one is 0. That does imply measurement. Yes?
If that was just 1.08, would it still be 1.08 times 10 to the power of 0?
Mm-hmm.
Would that be?
Yeah, if the original number here was 1.08, and you had to write that in scientific notation, it would be 1.08 times 10 to the 0. If there was not this trailing 0 in the original number, you definitely would not just throw 1 in. The nice thing about scientific notation is when you write it in scientific notation, all the digits in the decimal part are significant. So, we put this number in scientific notation and those pesky zeros disappeared. Okay, let's look at this one. 2,371. How many sig figs? 4. That one's easy, huh? How about 2.97 times 10 to the 5? 3. Scientific notation, we're only going to look at the decimal portion. There will be no leading zeros. There will be no trailing zeros without a decimal point. And so if you have any zeros in there, they're always going to count. This times 10 to the 5 takes care of those place-holding zeros. What if we wrote that number in decimal notation? We're going 1, 2, 3, 4, 5. So that would be the same as 297,000. In this number, which digit is uncertain?
7.
The 7. It's always the last significant figure. So there was uncertainty in the 7. That was estimated. In this number, 297,000, as it is written there, these zeros, trailing zeros without a decimal point, are ambiguous. We're not sure if they're just there to hold the decimal place or if they actually mean that, yeah, we measured to the nearest 1 foot or whatever it was. Does that help at all? And so we want to be careful how we write things. When we've got trailing zeros like this, it's always better to put it in scientific note. Is that a new section? I don't know.